Assalamu alaikum wa rahmatullah. Welcome back. So we continue our discussion on congestion control mechanisms for virtual circuits. We talked about three mechanisms: admission control, careful routing, and resource reservation. And now we would like to continue with congestion control mechanisms in datagram subnets or in networks that apply connectionless services. Now, in connectionless services, we don't have a reservation of a specific path. However, a larger message gets divided into smaller packets, and then packets carry the full source and destination address. And then eventually, each packet will get delivered, will get routed independently through the network, possibly different packets taking different paths. Now, in this case, what can we do to avoid congestion? So, our general idea is that routers inside the network monitor the utilization of their outgoing links. So imagine a router in the middle of the network and its outgoing link. So we have a router in the middle of the network. We have its outgoing link. That router monitors how much is this link used. So again, this router is monitoring how much this link is used. And if the router notices that the link is too busy, it will basically initiate a warning state for this link. It will declare that this link is being congested or close to being congested. Now, the job of the router, again, let's not forget that this is the router and this is the link. Sorry for the handwriting, that's the best that we can achieve. And this is our dot for link. Now, we wanted to say that once the router declares the link congested, it will basically try to inform the senders. We have some sender far away. So imagine this is a sending host far away from the router. And basically, the router would like to inform the sender to slow down. Now, how does the router inform the sender? We have three mechanisms that we'd like to talk about, and after them, actually, we have a fourth nice mechanism. The first one is called the warning bit, and the second one is called choke packets and hop by hop choke packets. So let's see how the warning bit works. The warning bit works as follows. In the packet header, we have a special bit that we call the warning bit. The default value for this warning bit is 0. So any packet that starts traveling in the network has a 0 value in the warning bit. Now, if this packet travels through a congested router, the congested router would forward it to the destination. However, before forwarding, the congested router would change the warning bit value in the packet's header from 0 to 1. As if we are marking this packet, anyone who sees it with the warning bit equals to 1 would know that this packet went through some congested router. Now, when this packet arrives at the destination, as you know, the destination needs to respond with an acknowledgement packet, and the acknowledgement packet has a header as well. And in the acknowledgement header, there is also the warning bit that will be copied and it will become 1 as well. Now, when this acknowledgement arrives at the receiver, sorry, when this acknowledgement arrives at the sender will notice that the warning bit is raised to 1, so it would know that its original packet went through some congested router. It means that the sender will decide basically to slow down transmission for future packets. It will slow down the sending rate for the future packets, and this is what we call the warning bit. The next technique is called choke packets. It's similar to the warning bit. Again, it's similar to the warning bit in the sense that the router monitors the outgoing link. If a router inside the network, if a router in the core of the network notices that the link is congested, notices that its outgoing link is congested, the router would basically send immediately a special packet that we call the choke packet back to the sender. So that choke packet will be sent immediately back to the sender. And when the sender gets a choke packet, when the sender receives a choke packet, it will know that its original packet went through some congested areas. Again, it will decide to slow down. Now, this picture gives you a little bit of the idea and also a timing diagram. So what happens here is as follows. We have router A sending packets going through EF until router D. Imagine that router D becomes congested. It means that at that time, so we can think of these pictures as different things happening at different times. Going back to this time, router D will send a choke packet. However, it has sent a choke packet. It does not mean that it will be relieved immediately simply because the original sender is router A. Router A is still sending at a fast rate. It means that even though the choke packet has been sent by D, it is still receiving packets at a fast rate. Now, this choke packet will travel along the reverse path. So, this is the choke packet. It arrives at E. Now, from E, it will arrive at A. Now, at that time only, router A knows that router D is congested, and now it will start sending at a reduced rate. So if you look here, this says reduced flow. At that time, the sending rate of router A has been reduced. It has a lower data rate, lower bits per second. Of course, that reduced rate will take also some time until it gets reflected at router D. So this is what we would like to say. Router D got congested, it sends a choke packet. However, the effect of relieving D will take some time. It will take the time for the choke packet to travel back to the actual sender, and then it will take time for the reduced flow to take effect basically over this link and then this link and then finally over the last link. And this is when router D gets relieved from congestion. And this motivates us with our next mechanism, which is called hop by hop choke packet. In this mechanism, on the same diagram, what you see on the right here, what you see on the right is basically the hop by hop choke packet as opposed to the normal choke packet operation. Hop by hop choke packet, let's say we have the same idea, we have the same example. There is router A sending packets to router D. It is sending packets fast here. So this is a fast transmission, fast transmission, fast transmission. Now router D gets congested. According to the choke packet mechanism, router D will send a choke packet. Router D will send a choke packet back to the sender. However, the choke packet will have to travel from D to E. Now look what router E will do, and this is what we call hop by hop choke packet. Router E will reduce its transmission immediately. Yes, router E was not the original sender. The original sender was A. However, once router E here gets the choke packet, it will send at a reduced rate immediately. So this relieves router D immediately. However, it will take some time until the choke packet arrives at the original sender. Then the original sender will slow down, and this is basically when router D will get relieved for real. Now, what happened here exactly? What happened is that the next router, which was E, decided to reduce the sending rate immediately to relieve the congested router, but this comes at a price. Of course, the price that you can imagine is that router E is forwarding slowly. However, it is still receiving packets at a fast rate from the original sender, which means that router E here needs to allocate more buffer space. So the difference between the packets that come in fast and the packets that need to forward it slowly, that difference of packets need to be stored, and that router needs to allocate more buffer space. Now, when does the router not need this buffer space anymore? This happens when the original router slows down once the choke packet arrives, and then things will be all right. So this is the hop by hop choke packet example. And finally, we have one more mechanism, which is basically very famous. It was invented in 1993 by Floyd and Jacobson, so not that long time ago. However, still not new. So how does that work? It works as follows. Again, the routers monitor how congested their outgoing links are. So the routers monitor how congested the links are, and the simplest way to do it basically is to count how many packets are waiting in the buffers to be sent over the link. Now, if the router notices that the buffer is empty, it does not have too many packets waiting. It means that the outgoing link is not congested. Oppositely, if the router notices that the buffer has a lot of packets waiting in the queue, waiting in the buffer to be sent, this is an indication that the outgoing link is congested. Now, the way it is done exactly is that the router maintains an estimate of the average queue length on average during the past time. On average, during the past time, what was the length of the queue? How many packets were waiting inside that queue? And if this length is found to exceed a threshold, so we will not be waiting until the buffer gets completely full. No, we will not do that. If just the size of the queue, if the number of packets waiting in the queue exceeds a threshold, we would declare that the outgoing link is congested. And now this is the smart action that happens. What the router does in this case is that it will choose one of the packets waiting in the buffer at random to drop it. Just drop it. Refrain from forwarding the packet. So, which means that this packet will not arrive at its destination. If a packet does not arrive at its destination, what does that mean? It means that the destination will not send an acknowledgement. Now, basically after a timeout period, the sender will notice, the sender now, the source, will notice that the acknowledgement did not come back, which would be a sign that along the way the original packet got lost because of congestion. Now, what the sender will do in this case, what the sender will do in this case is that it will decide to slow down transmission. So for its future packets, it will send these packets at a lower rate, at a smaller amount of bits per second. And this is what happens. Basically, we call it random early detection because the router, once a link becomes close to congestion, it will pick a packet at random to drop it. The reason for picking a packet at random is that the router would not know exactly which exactly is the sender that is causing congestion. So it picks one at random, and then the corresponding sender needs to slow down. We call it early because this effect is introduced only after exceeding a threshold. So we're not waiting until the buffer gets completely full. As you know, if the buffer gets completely full, it means that future packets will get dropped naturally without doing anything. Future packets will just not find a place to wait in the buffer, and then they will be lost. If they will be lost, acknowledgements will not come back, and the sender would know that congestion has happened along the way. Now, according to this technique, random early detection, the router is introducing the same effect as a lost. The router is introducing the same effect as a lost packet. However, it is doing that earlier, just after exceeding a threshold. It's quite a smart idea. Of course, that packet got lost. It means that it needs to be retransmitted later. However, with the future transmissions, the sender is also slowing down. Now, one important comment is that what happens at the router of measuring the queue size, deciding if it has exceeded the threshold, and also deciding to pick one packet at random to drop it, all what I just explained happens at the router. So this is considered as a network layer mechanism. Now, what the source does accordingly is to slow down. Now, the details of slowing down by how much percent, when to speed up again, and all these details, this happens at the sending host. And these details are really part of the transport layer. So when we talk about the transport layer later, we will come back to this about congestion control again, but exactly, I mean precisely focusing on what happens at the host side, at the sender side. So thank you so much. And our next topic would be quality of service. Until we meet again, thank you very much. Assalamu alaikum wa rahmatullah.